Alright, hello class. So in this video we are going to continue our discussion on partial fractions and talk about some of the situations that pop up that kind of complicate things. One comes from the natural question of, well, what happens if you can't factor the denominator all the way, right? Can you still go through this process? The answer, of course, is yes. And it also turns out that that if we have repeated factors, there's also a bit of a thing we have to do to deal with that. Okay, so let's start with the repeated factors, just to kind of show how that works and how that changes things. And then we'll talk about what happens if you can't factor the denominator completely. Okay, so why we have to concern ourselves with repeated factors is if we add two fractions where one denominator is just maybe the other one squared, to get the common denominator, you just multiply the first one by, say, x over x in this particular case, and you would get x plus 1 all over x squared. Okay, now this, if I now go back and take this out, when we split this up with partial fractions, we go from a denominator that's just x squared to then two pieces, 1 over x and 1 over x squared. Okay, so we didn't have to concern ourselves in this direction. But when we set up the partial fractions, we need to basically take into account both possibilities, the x and the x squared. So completely factored, this is x times x, right? So we don't do, say, a over x plus a over x. When we split this up, it's a over x plus a over, oops, not a, but b over x squared, okay? And it just comes from the fact that it's possible that you can add things like this together and get a repeated factor in the denominator. Okay, but from here, it essentially follows the same way in our partial fraction. So this is the partial fraction direction. Right here, we would multiply by the x squared. Okay, well, when we do that, things cancel. So I'm going to leave myself some room. Okay, so here the x squareds cancel completely. Here, just one of the x's cancels. So this x cancels with one of those and just leaves an x. And then the x squared, where's my cutter? There it is. Here cancels completely. Okay, so we get down to x plus 1 is equal to ax plus b. And here, I would not actually bother doing strategic values. I would just match coefficients, because if ax plus 1 is, if ax plus b is equal to x plus 1, this can only happen if the 1 here is equal to the a, and the 1 here is equal to the b. Right? So matching these together logically tells me that a is equal to 1 and b is equal to 1. Right? Which is what we started with. That's not a surprise, I hope. But this is just to show with a real simple example why we need to consider both possibilities. Okay, so whenever you have a repeated factor, so if you factor it all the way down and you get something squared or something cubed, you need to actually take care of all possibilities. So if you have some stuff in the numerator, and say you have x minus 1 to the 5th down here and maybe an x, well, when you break this up as a partial fraction, you need an a over x minus 1, you need a b over x minus 1 squared, a c over x minus 1 cubed, a d over x minus 1 to the 4th, a c over x minus 1 to the 5th, and then a d over just x. Okay, so you need 1 for every possible thing going from to the 1 power, which is what we have here, all the way up to the 5th power, which is what we started with. Okay, so let's look at an example that is a little, more complicated than this one. Okay, so yeah, let's do that. Okay, so here we have 5x squared minus 3x plus 2 all over x squared times x minus 2. So always our first step is to factor, but since this is completely factored already, I'm going to go ahead and just start with the partial fraction decomposition. So since we have a repeated factor here, okay, we're going to, well, repeat the factor. So we'll need an a over x plus a b over x squared. Okay. Then we have this factor, which is just, a single linear factor, so that will just get a c over x minus 2. Okay. Then we multiply by this x squared times x minus 2. And so this it cancels all of this completely, this original denominator, right? So we'll get 5x squared minus 3x plus 2. And I'll go ahead and write it all out this time. We'll have the a over x times the x squared times x minus 2 plus the b over x squared times x squared times x minus 2 plus c over x minus 2 times x squared times x minus 2. You can also think of it as you're just taking this denominator and moving it over, but you have to multiply everything by it. So the thing here is that this x cancels with one of these x's. This x squared cancels with this entire x squared, and this x minus 2 cancels with this x minus 2. Okay, so let's write what we have now. This side of the equal sign doesn't change. We'll have a times x minus 2. Here we'll have b times x minus 2. And here we'll have c times x squared. Now the problem here with doing strategic values is we won't get everything. Okay, if we plug in 0, it will cancel out our a and our c, leave a b, that's fine, we could solve for b. And then if we plug in 2, it will cancel out the a and the b and leave c, so we can solve for the c. Then we'll have an a. Okay, so in these cases with repeated terms, you usually have to either match coefficients or do a mixture. Okay, so with repeated terms, you usually have to match coefficients at some point. Okay, but you can do a mixture. Or do an even more strategic value. We'll talk about that in a second, but sometimes a mixture is the best way to go. So what I mean by that is, so we'll start with the 0 as our first strategic value, right? So that cancels these guys out. We'll be left with a 2 is equal to a times 0 plus b times negative 2 plus a c times 0. All right, so these guys 0 out. We get that 2 is equal to negative 2 times b, which tells us that b is equal to negative 1. Okay. Now our next strategic value would be 2, because 2 will cancel this and leave this c. All right, so we'll get 5 times 2 squared minus 3 times 2 plus 2 is equal to a times 0, because that 0's out there, plus b times 0, plus c times 2 squared. Okay, so it cancels these two guys out, but leaves a c. All right, so far, pretty much the same. Right, so here we'll get 5 times 4, so that'll be 20 minus 6 plus 2 is equal to 4c. Okay, so that will be a 20 minus 4, so that will be a 16 is equal to 4c. So when we divide through, c is equal to 4. Okay, so far so good, but we've run out of strategic values. There's nothing that will cancel out the b and the c but leave the a. Okay, so the strategy here is put these values back in. So put the found values back in. And then you're either going to match coefficients, or you can also put in another strategic value if you want, and you'll just have another equation to solve. So let's start by putting the values back in. Okay, so we'll have this 5x squared minus 3x plus 2. That doesn't change, right? The a is what we're still looking for. However, we know what b is. B is -1, so I'm going to put a -1 in and just distribute it across to get -x plus 2. Okay, and then we'll get plus 4x squared. All right, so now we actually have a more simplified equation to deal with, since we don't have a b and a c. So we can actually start moving things around. So if we subtract this 4x squared over here, the 5x squared minus 4x squared will just give us x squared. Okay, bring that x over, we'll get minus 2x, and then the 2's just cancel outright. Okay, and actually, if I were to distribute this x across here, we would get a times x squared minus 2x. And look at that. That's exactly what we have here. And since I have a 1 out front here, these two need to match. Okay, so this tells us that a has to be 1. All right. There are other ways we could do that. What we could do is, if we wanted to fully match coefficients, so if we just didn't see this, we wanted to match coefficients. Okay, you have your x squared minus 2x is equal to, if we distribute this across, is ax squared minus 2ax. Well, our x squared coefficient is 1, and so that means 1 needs to match up with a. So once again, we still get a is equal to 1. Okay, you can also plug in a value. Okay, so if you plug in another value, so if we go back to say here, okay, here. So let me write this again. I have x squared minus 2x is equal to, let's say I didn't distribute. Let's say I had it like this still. Okay, I had x squared minus 2x is equal to ax times x minus 2, and I didn't automatically see that that just kind of goes away and gives me the a is 1. We can plug in another value we haven't plugged in yet, right? We plugged in 0, we plugged in 2. We could also just plug in something like 1. Right? If we plug in 1, we'll get a 1 minus 2 is equal to a times 1 times negative 1. So we'll get negative 1 is equal to negative a. So once again, a is 1. So however you go about it past this point, okay, you will still get that a is equal to 1. All right, so whether you want to just match all the coefficients from the beginning, or you want to plug in strategic values, then match or do whatever you can to simplify it down and figure it out, you can. So that's what I mean by after this point, you can either match coefficients or you can do a mixture of things that will all work as long as every little thing you do is correct algebraically. Okay, so that brings us to, right, a was 1. Okay, b was negative 1. And then c was 4. Okay, now what we really need to be careful about is don't get so caught up in the natural log stuff that you forget that this guy's not going to be a natural log. All right, so once again, let me clean this up and then I'll show you what I mean by that. Okay, so definitely watch out for this because this will be a natural log of x. This will be a natural log of a absolute value of x minus 2. This will not be, because if we rewrote that as 1 over x minus x to the negative 2 plus 4 over x minus 2, this is just going to be a power rule. Okay, so that's something I see a lot, is people just saying that this is the natural log of x squared, but that's not how this works at all. So this is just a power rule, while these guys are our natural logs. All right, and so from there, we'll get the natural log of absolute value of x. Here, we will get x to the negative 1 over negative 1, okay, plus 4 ln absolute value of x minus 2 plus c. Okay, so I'll do what we've been doing before. I'll move the 4 up, bring these two together, and just simplify the power function here. So what we'll end up with is natural log of the absolute value of x times x minus 2 to the 4th, okay, then plus, and we could write this as 1 over x if we wanted to. I'll go ahead and do that, plus c, and there we go. Okay, so there is an example of repeated factors. Okay, now the next tricky thing that can pop up is when things don't factor all the way. Okay, so let's take a look at that. Okay, to show an example of what I'm talking about when I say things that can't be factored, is say if we had something like this in our denominator. So, you know, I have my x minus 1 thing showing up, and then I have this x squared plus 1. Now this can't be factored. This is reduced as far as it can, and it's an irreducible factor. Specifically, it's an irreducible quadratic factor. Okay, and how we handle this is we still do our, a over x minus 1, all right, for that first linear factor. But then for the second one, since we can't actually factor this guy, what we're going to do is not just put a constant over it, but we're going to put a bx plus c over it. Okay, and we do that because notice for a linear factor, the polynomial that's 1 degree below it is just a constant. If you have a quadratic, this is degree 2, and this is degree 1, right? You're putting a polynomial of degree 1 less than what you have in the denominator. So here, this is a degree 1 to start with, and what we're doing is we're putting a degree 0 polynomial on top of it. Okay, so that's how we always tackle these things. So if you had a cubic, like if you had a degree 3 polynomial that couldn't factor down any further, you'd put a quadratic over it when you're doing partial fractions. Okay, but from there, it follows the same way. Okay, we will multiply everything by this full denominator, right? The x minus 1 times x plus 1. All right. And what ends up happening, it's a little simpler than with the repeated as far as things canceling, because the full x minus 1 cancels and the full x squared plus 1 cancels, but the result is a little trickier. So here, this doesn't change. The whole denominator on this side always goes away. All right, so we'll just say this. Then I'll write it out explicitly. All right, it'll be a over x minus 1 times x minus 1 times x squared plus 1. So the x minus 1's cancel. Then it will be plus bx plus c over x squared plus 1 times x minus 1 times x squared plus 1, and here the x squared plus 1's cancel. Okay, so we're left with x squared plus x plus 2 is equal to a times x squared plus 1 plus bx plus c times x minus 1. Okay, and here's where things get a little different, because we can plug in a 1 here to cancel this all out and solve for our a. We could do that, without much trouble. But then we're going to have to end up having some sort of system of equations anyway. All right, so what I'm going to do is with these, whenever I have something like this, what I end up doing is I just end up distributing and simplifying this as far as I can, and then I just match coefficients. Okay, when it gets more complicated, I just go straight to matching coefficients, because when everything's a nice linear term, it's no problem, but when things like this start showing up, I mean, you might as well just jump to the one that will always work. Okay, so what I'm going to do is give myself a little more room here. Then I'm going to distribute this a across, okay, to get ax squared plus a. Then I'm going to FOIL this out completely. So when we FOIL it out, I'm going to get bx squared, okay, minus bx, okay, then plus cx, then minus c. And then I'm going to collect all of my like terms, because for x squared, we have an ax squared and a bx squared. Okay, so in my next step, I'm going to write x squared, and over here, let me make the equal sign in white. Over here, I'm going to say that I have an a plus b x squared. So really, I'm factoring the x squared. I'm bringing these together and factoring out the x squared. Okay, so I have a 1x squared. Then I'm going to collect my x's. Well, my x's live here. I have a minus bx plus a cx. Okay, so when I bring this together and factor out the x, it will be a minus b plus c times x. Okay, and so that needs to align with the plus 1x over here. And then I'm going to collect my constants. Well, I have an a here and negative c here. So it will be plus a minus c. Let me go ahead and put that in parentheses because that needs to match with the 2. Okay? So when we match coefficients, this 1 needs to match the a plus b. That's the only way this can work. So I'll say that 1 is equal to a plus b. Okay. Then for the x term, so that's, let me write that here. That's the x squared term. All right. Then the x term, which we did in pink, that 1 needs to be equal to this, negative b plus c. So I'll say it's c minus b. And then in green, we have the constant. So I usually write this as const. And so this 2 needs to match a minus c. Okay, now there's another way we can actually solve these. So here, if I look at these two, I'll see I have a b and a minus b. So if I take a equals a plus b, or sorry, 1 equals a plus b and 1 equals c minus b, I can actually add these together and get that 2 is equal to a plus c and the b's cancel. Well, does that actually help at all? Well, if we bring in this particular line, I have that 2 is equal to a minus c. And so we can add these two lines together, and now the c's will cancel. So I'll get 4 is equal to 2a. Okay, which tells us that a is equal to 2. All right. Now, from here, we can just start plugging back in. If a is equal to 2, then let's take that and plug it into this a, which tells us that 2 is equal to 2 minus c. Well, that tells me that the c's, or the 2's cancel, so c is equal to 0. Okay, and then we can take this c and plug it into one of our other equations that we have. So let's plug it into this one we started with in pink, plug it into there, so we'll get 1 is equal to 0 minus b. So this tells me that b is equal to negative 1. Okay, and that, I think, is all of our letters, right? So we have a is 2, c is 0, and b is negative 1. Okay, so if we go up here, we can now plug in our values. So I'm going to take a second and clean this up and be back in just a minute. All right, so we found that a was 2. So let's put in 2 for our a. We found that b was negative 1. So let's put that in here. Okay, and then we found that c was 0. So I'm actually just going to write plus 0 there. Okay, so this actually simplifies out to 2 over x minus 1 minus x over x squared plus 1. All right, so let's put this in an integral and integrate it. Okay, so once we stick this in an integral, this is our usual ln stuff. Okay, nothing different there. Here, we need to be kind of careful. In this case, it is going to be a u substitution. And I'm going to use a quick u substitution for this. It's mainly because the derivative of the denominator is 2x, which is almost what we have here. Okay, so let me write that as I'm going to do a quick u. So to think about how we're going to do that, think of this as x times 1 over x squared plus 1. And whenever you have 1 over the stuff, times something like the derivative of this stuff, you can use a quick u substitution. Okay, so this piece is going to be 2 natural log absolute value x minus 1, okay, minus, I'm going to write that x, I'm going to say it's the natural log of the stuff, x squared plus 1, but remember we need to divide by the derivative of the stuff. So that's going to be 2x. Okay, so the x's cancel. And remember that you can only do this if the x stuff cancels. Okay, so we have 2 natural log x minus 1 minus 1/2 natural log of absolute value of x squared plus 1. Now, we can actually drop the absolute value bars here because this will always be positive. This is always greater than 0, right? Always, because we're taking something, squaring it, making it positive, then adding 1. So we don't actually need to worry about the absolute value bars. And then here, when we bring in that squared, we can drop the absolute value bars there. Okay, so we're going to bring in the exponents and we're going to join these with division. Okay, so our final answer is going to be, oh, that is not the color I meant to grab. Our final answer is going to be the natural log of x minus 1 all squared all over the square root of x squared plus 1. And I know I've said it multiple times, but this is mainly just so you can check your answer, or if you're choosing a multiple choice, this will work as a final answer. Okay? All right, now let's look at another example that mixes all these things together. Okay, so here's an example that should combine these two techniques together into one problem. And may end up being kind of a pain to get through, but here we have a repeated factor. Okay, and then here we have a irreducible factor, or you could call this a prime. Sometimes that's what we call this, a prime factor, because we would need factors of 2 that would sum up to be 2, which is not going to happen because the factors of 2 are 2 and 1. So if you had a 3 here, you could factor this, but since we don't, we have to, well, use our form of partial fractions that puts a linear term over it. So here, since this is a repeated binomial, you'll get a over x minus 2 plus b over x minus 2 squared plus cx plus d all over this unfactorable quadratic. Okay. Now, from here, we're going to multiply by this thing. All right, now I'm not going to write it all out this time because we will really run out of room, but just note what things cancel, right? So here, the 1x minus 2 cancels. So we'll get a times x minus 2, okay, times this x squared plus 2x plus 2. Okay. Here, for the b term, both x minus 2's cancel. So we'll be left with x squared plus 2x plus 2. Okay. And then here, for the cx plus d, the whole thing will be multiplied by, well, the x squared plus 2x plus 2 thing cancels, so we're left with the x minus 2 all squared. Okay, so this is a bit of a mess, but we can hopefully handle it. There are ways we could go about doing this. What I'm going to do is I'm going to try and do a mixture of techniques for this one. So I'm going to start by plugging in 2, because to me that seems like it will simplify some things. So let's plug in x equals 2. Okay, so we'll get 10 is equal to, this part zeroes out. We'll get b, so it'll be 2 squared plus 2 squared again, plus 2, okay, plus the cx plus d term, and it zeroes out. Okay, so we're left with just 10 is equal to b. That'll be 4 plus 4 plus 2, so that will be 10 is equal to 10b, so b is equal to 1. Okay, so we could put a 1 in there for that. Okay, now that is fine. There's not another thing we can plug in that will actually like really simplify what we're doing here. So now I'm going to take what we have and simplify it down a little bit. Okay, so the 1 just makes this x squared plus 2x plus 2. Okay, then plus cx plus d times x minus 2 all squared. All right. So now I'm going to move all this stuff here over to this other side. Right, so I'll get a negative x squared minus 2x plus 8 is equal to a times x minus 1 times x squared plus 2x plus 2 plus cx plus d times x minus 2 all squared. All right, now I'm going to start plugging in some other stuff to, we could multiply this all out, but I honestly don't really want to do that. So that's definitely not what I meant to do there. So what I'm going to do, okay, stop doing that. I'm going to start plugging in some other values. So we plugged in 2. Let's plug in 0. Okay, when we do that, these guys zero out, so we'll get 8 is equal to a times negative 1, right, when we plug in 0 there, times 2. Right, then here, notice that 0 cancels out the c. Right, so we're just going to get an equation now of a and d, and then times negative 2 squared. So we get 8 is equal to negative 2a plus 4d. And to simplify things, I'm going to divide all this by 2 so that I get 4 is equal to negative a plus 2d. All right, I'm going to save this equation. All right, I'm going to call this equation 1. All right. Now, let's plug in 1. Now, there's no magic to what I'm doing here. I'm just picking easy values, right? Sorry, I totally messed something up here, didn't I? These should be 2's. Sorry about that. Yeah, I did get this part right, though. No, I didn't. That's negative 2, so that will be negative 4. So that will, instead, I'll divide this by 4. So that I'll get 2 is equal to negative a plus d. I am sorry about that. Glad I caught it, though. All right. So now, let's plug in a 1 and see what happens. Notice I can't plug in a 2 again because I'll just get 0 and 0 here, and you know that's not going to help. So let's plug in a 1, and I'll get negative 1 minus 2 plus 8 here is equal to a times negative 1 times, here I'll get a 1 plus a 2 plus a 2. Okay, then here I'll get a c plus d times negative 1 squared. Okay. So here we'll get 5 is equal to negative 5a, right? Because that's a 4 plus a 1 times a negative 1. All right. Then here, that just becomes a 1, so we'll get plus c plus d. Okay, now we have an equation with a and d, an equation with a, c, and d. And let's do one more. Let's say I put in negative 1. So again, I'm just picking, this might seem like a really messy process, and these do get messy real fast. Okay, so let's put in a negative 1 and see what we get. So when we put in a negative 1, we'll get negative 1 here again, but it'll be plus 2 plus 8. Okay, equals, now, oh gosh, where's my original equation? Here it is. Let me, there we go. Okay. Now, this will be a times, that'll be negative 3 times, that will be a 1 minus 2 plus 2 plus a negative c plus d times, now this will be a negative 3 squared. All right, I promise we're getting there, okay? So here we'll get a 9 times, that will be negative 3a, and here that will be plus, this will be a 9, and I'm going to factor that out. So it will be a minus 9c plus 3d. Okay, so what can we do with all of this? Well, we are going to hopefully break this down in some way. So we have an equation 1, we have an equation 2, and we have an equation 3. Okay, so equation 1, we can solve for d. d is actually 2 plus a. Okay, so we can replace d with 2 plus a here and here. Okay, so then equation 2 becomes 5 is equal to negative 5a plus c plus 2 plus a. Okay, so if we move that 2 over, this gives us that 3 is equal to negative 4a plus c. Okay, now if we plug the 2 plus a, okay, a couple ways we can go from here, but if we plug the 2 plus a into this d, equation 3 becomes 9 is equal to negative 3a minus 9c plus 3 times 2 plus a. Okay. All right, then we can simplify this down to be 9 is equal to negative 3a minus 9c plus 6 plus 3a. Oh, and look at that. Those 3a's will cancel if I've hopefully done that right. All right, this 3a will cancel with that 3a, and I think we are now in business because if I move this 6 over, we'll get that 3 is equal to negative 9c, which tells me that c is equal to negative 1/3. Okay, now So that was from equation 3. All right, give that a big old circle. Now, I'm going to plug this c back into this equation. Okay, so then equation 2 becomes 3 is equal to negative 4a minus a third. Okay, so now I want to multiply by 3, and I'm doing that just to get rid of the denominator here. So we'll get 9 is equal to negative 12a minus 1. Okay, so moving that 1 over, we get that 10 is equal to negative 12a. So a is negative 10 twelfths, which is negative 5 sixths. So that's our a. Let me write the completely simplified version here. And we're almost done. Now I'm going to go back to here because d is 2 plus a. Okay, so d is 2 plus a, and now I can take this value and plug it into my a. So d is equal to 2 minus 2 sixths, and here 2 is, no, what am I doing? That's 5 sixths. Sorry about that, 5 sixths. So we get 12 sixths minus 5 sixths, and that will be, what, 7 sixths is our d. Okay, so hopefully you get the sense now how nasty these things can get when we don't have all these nice linear factors. Okay, but when we get to this point, okay, we just put our values in, and they just, you know, they just happen to be fractions here. Okay, so let's see what our final result would be here. Okay, so when you put the points or the values back in, I put the crazy fractions off to the side here. So we get this. Now, I don't want to, you know, this was already a long enough example, but what I do want to mention is that when you get to integrating these things, so when you get your, say, ax plus b over something that can't factor, your little ax squared plus bx plus c, often you'll want to break it up. So when you integrate, you want to do this piece, which will likely be like a quick U substitution. Sometimes together they make a quick U substitution. But often you'll need to split it up. So actually, let's take a look at just this piece, how we would integrate that. Okay, so let me just put that in an integral. What I'm going to do to start with, though, is I'm going to simplify this so that I don't have fractions up in here. I'm going to move it out as a single integral. So just so we can see how we would tackle one of these more complicated guys here. Okay, so I know this example's gotten real complicated already, but a lot of Calculus 2 is doing really tough integrals, right, and dealing with really tough situations. So how we would go about this is actually, I would want to split this into a U substitution and hopefully something else. And we'll see if we can actually get that something else that we need. Okay, so what I mean by that is if I were to let the denominator be my u, right, x squared plus 2x plus 2, then du would be 2x plus 2. Well, I almost have that. Other than a minus sign, what we actually have is a 2x plus 7. Okay, so what I'm actually going to do is, if I negate this, I would get negative 2x minus 2. So what I really want for the u substitution is this, negative 2x minus 2. Well, I could put a minus 2 in here, but then I would need to add a 2. So this is our funky version of 0 idea. Okay, so what we would do is I would say this is negative 2x minus 2 over this denominator. Okay, then what I have left is the 7 plus 2. So I would have a 9 over just this thing all by itself. Okay. Now this we could tackle with the u substitution that we just set up. Right? Because this is going to be a du, really a negative du over u. Okay, so we'll do this with a quick u substitution. I'll show that in just a second. And then this, well, this hopefully looks similar to some of the things we were doing before, where we can complete the square. Right, because we almost have a perfect square. If this was a 1 instead, well, what we're going to do, and let me clean this up. All right, so this part, again, we're going to do with a quick u substitution. So what I'm going to do is write it like this. It's negative 2x minus 2 times 1 over this stuff here, x squared plus 2x plus 2. Okay, then here I'm going to complete the square, because this, let me write it over here in green. If I break up this 2 as a 1 plus 1, this part will factor as x plus 1 all squared. Okay, so this, okay, this is a tan inverse pattern with an x plus 1 instead of just an x. Okay, so this is a tan inverse of x plus 1 over 1 pattern. All right, so now we'll just crank this out. We'll get a 1/6 times, I'm going to rewrite this negative 2x minus 2, and then I'll have the natural log of this stuff, absolute value, okay, all over, now I need to divide by the derivative of the stuff, which is 2x plus 2, and these will cancel, but we'll leave a minus sign. Okay, so that will leave a negative 1 sitting out here. And then this is just going to be that 9 comes along for the ride. Okay, then we'll have tan inverse of x plus 1, which that that's all because our a here is 1, right? So we can we don't have to worry about the dividing and all that stuff. Close this off, give us a plus c, and that is pretty much it. We can distribute this 1/6, but I mean, other than that and some simplifications, that's basically it. Okay, so when we multiply the 9 by the 1/6, we'll get 3/2 tan inverse x plus 1. And honestly, after all that, I would leave it like that. Okay, now I don't want to melt your brain with some more examples, but one last thing I just want to mention, and you know, this all works in pretty much the same way, but if you have a repeated factor, so this is repeated, because we're cubing it, and irreducible, so I'll just say and prime, well, we do just like we did before. We need an ax plus b for just the x squared plus 4. Okay, we need a cx plus d for x squared plus 4 squared. All right, since it's a repeated prime factor, then we need a ex plus f for an x squared plus 4 cubed. So we need one for each possibility to the 1 power, squared and cubed, and since these are all irreducible quadratics, we need to put a linear function above them, an ax plus b, cx plus d, and ex plus f. Other than this, right, it basically all works the same way, just trying to solve for your variables in the easiest or best way you possibly can. Okay, so I really do think that's enough for this video, and I will catch you all in the next one. Cheers.